It's okay?
Yeah. O resultado que a gente quer. consegue rodar aí, velho? Que o negócio, eles estavam fazendo demais, e eles só
passo a passo, já tem os dados, aí a gente vai montar um novo material, ele vai fazer a mesma experiência e vai coletar os dados. Mas vamos supor que você tem uma experiência que você não tem na biblioteca do GEANT4, você vai ter que programar toda ela.
até a geometria. Tipo, como se fosse
eu achei que você tinha sempre desenvolvido uma biblioteca que você já pudesse baixar ela e fazer as comparações com aqueles dados que você precisa.
Não, mas até o próprio
Essa modelação que a gente está fazendo aqui, ela é iniciada, essa pista, já que a gente pode fazer no laboratório, porque se não for, a gente está gastando uma esforço enorme.
Normalmente comparar uma coisa no chão. Você vai simulação e é desconfiável. Você vai compositar. Esse mais ou menos agora o meu trabalho já só que eu fiz essa parte que eu trabalho no Polícia Federal, que a gente lida nessa parte de ameaças da jardim, então eu não tenho essa visão assim, de problema, igual você já mostrou agora. Eu não tenho visão de situação, porque agora você está mostrando isso. Vou levar um tempo até chegar nesse nível, você tá, de programação, mas pelo menos no geralzão você dá uma.
So I think now I have kind of 20-25 minutes of lecture, and then we stop for the coffee break, and then we resume with another short lecture, and then it will be exercises up to the hand. So far we saw the mandatory ingredients of GEANT4. More or less you have seen the geometry, you have seen how to set a primary particle and how to select a physics list. So this is what is really required to have a running GEANT4 simulation. Still, at the end of the day, it's not what you really want, because you also want to get an output out from a simulation. You don't want to just track particles in a volume, but you want to retrieve some kind of information. And this is what the lecture today is about. This is typically the most tricky part of GEANT4, because when you have something which is very flexible, usually it's also very complicated. So you can do more or less everything, but the price to pay is some extra difficulties, complexities. So there are a few tools in GEANT4 that can make life a bit easier for new users. So if you have to do something which is pretty common, GEANT4 is already providing some tools that are ready for the use. So now what we are talking about is those optional classes that gain control of a GEANT4 simulation at various stages. So run action, it's what is performed before and after each run. Event action is what is performed before and after each event. Stacking action is called every time you register a new secondary. Stepping action is called every time you have a step. So depending on the actions that you want to perform, you have to put them into the proper class. So something which I didn't mention so far is the so-called stacking action. Which is the action which is performed when a new secondary is put in the stack. So you remember that when you generate, you are tracking a particle, and you generate secondaries, like you have an electron here that emits a ionization electron. So this electron is not tracked immediately, but it is put in a memory stack, and then is tracked later. Then you have another secondary emitted here, and this is put in a memory stack. And then when the primary, it's completely tracked, GEANT4 goes to the stack and tracks another of those particles. So when you generate a secondary, before putting it into this stack, you can perform some actions defined from the stacking action. For instance, if GEANT4 is trying to generate a secondary which you don't care about, you can just, okay, GEANT4, don't put it in the stack. Just forget about this, so that you don't have to track later. Suppose that you have a beta decay. So you generate a beta and you generate a neutrino. A neutrino you don't typically care about. It will just go away. So you don't have to track the neutrino. So that's a good place where you have a decay. GEANT4 will try to generate the beta. GEANT4 will try to generate the neutrino and the recoil nucleus. So you just say GEANT4, okay, just forget about the neutrino. I don't want to track it later. So the stacking action is called every time GEANT4 is trying to put a new particle in the stack. And this is where this is the place where you can select whether you want to track it or forget about that. And in some cases, this is useful to do, to save CPU time. Please.
Even if we don't define as a particle a neutrino, GEANT4 will account for this secondary particle.
Well, if you don't define the neutrino and then GEANT4 has a beta decay, GEANT4 will crash. It's because to close the kinematics, it will need to generate all the particles. Then GEANT4 will track all of them, unless you tell that you don't care about the neutrino, so you have to be killed. So all the particles, they have to be defined, otherwise GEANT4 will crash. So as I was mentioning the first day, all these classes are optional, in the sense that if you don't write anything in them, GEANT4 does nothing, but it's not mandatory to have them implemented. So also, you don't have to implement all the 5 of them. You implement only those that you need. For instance, you want to do something at every step, and you implement only the stepping action. And you take care of registering it through the action initializer. So you don't have to implement them all, but only the one that you need. For instance, in this case, the action initialization, you have the primary generator action, which is the mandatory, so you must have the primary generation. And in this case, you have only the event action and the run action, and that's it. You don't have the step action, for instance, because in this simulation you don't need, so you don't write one and you don't register one. So here it's really optional. You can do all of 5 of them, none of them, 2 of them, any combination. of those actions. So this is, let's say, a summary of what I already said. So what's a run, what's an event, what's a track, and what's a step. So the step in GEANT4, as was mentioned in the first day, it's a segment defined by two different interactions. So you are tracking a particle, you have a starting point, which is called the pre-step, and you have a final point, which is called the post-step. And the step is this segment, which the particle travels in a straight line. So nothing happens through the step, and the physics, it happens at the end of the step. So the interaction is happening at the end of the step. So you may also have geometry boundaries. So if you are passing from one volume to the other, the step can never cross a boundary. So this is because the properties of the two materials are different. So if you have a geometry boundary, the step will be forced to be on the boundary. So a step can never cross two materials. It's either in one material or in the other. So here, of course, there is no physics happening. It's just a technical stop. And then the next step is going into the new material. And then maybe you have an interaction here. So you then don't have interaction here, but you stop at the boundary because you have to recalculate the properties according to the new material. So this is a golden rule for tracking in any code, that a step cannot go through a boundary. So when you have geometry, you have to stop on the boundary and restart with a new step after. So from the conventional point of view, when you end a step into a boundary, this point belongs to the previous volume and this point belongs to the next volume. But this is just a convention. So if you want to check, if you enter, this is not interesting, and this is interesting for you. So how do you check that you are getting into the interesting volume? You check what is the volume of the pre-step, what is the volume of the post-step. If they are different, and the post-step is the volume interesting, so it means that you are at the boundary. So this is something that you typically want to have in the step action. You want to count the particles getting into the interesting volume. So the typical condition that you apply at the step action is if the pre-step is different from the post-step volume and the post-step is equal to interesting, it means that I am writing this in this position, so that I'm getting from another volume to my interesting one. So this is the typical condition that you use to check if a particle is getting into your volume of interest. So the pre-step and the post-step must be different, so it means that you are sitting on a boundary, and the post-step must be your interesting volume. So this is a typical thing that you do in a step action. So in some cases you want to know the flux coming into some specific volume, and this is the condition that you apply in the step action to have this logic implemented. So if this happen, count, or something like that. So it's just a counter of how many particles you get into your interesting volume. So as I was saying, that the step, which is a G4 step class object, it is made by 2 points, which is the pre-step and the post-step, and it's traveling, the particle is traveling a straight line between them. And the G4 step object, if you check the GEANT4 documentation, it contains the pre-step point, the post-step point, and all deltas. So you can check delta E, delta post, delta time. So if you want to check the variation of the properties of the particle between the pre-step and the post-step, you can ask to the G4 step object. And then you remember what is the G4 track instead. The G4 track is a photo of the particle which is taken after each step and which keeps the properties updated. So this is what I was saying before, that you can check whether you are on a geometry boundary by using this kind of condition, or you have also a flag which is called step status, which allows to do the very same. So this is something that it's typically you can typically do with within your step action. So from the step, you can get the track, which is the current updated information. So for instance, each track has a track ID, which is a number. The primary particle has track ID equal 1. All the others have 2, 3, 4, and blah, blah, blah. So if you want to check whether a particle is a primary or not, you just check if its ID is equal to 1. So if it's not equal to 1, it means that this particle is not the primary. It's a secondary produced by some kind of interaction. So if it's, you can check which was the primary which generated it and which process created that particle. For instance, you have an electron, secondary electron. This electron was created by whom? By ionization, by quantum scattering, by photoelectric effect. So you can check also which is the process which created that specific secondary. And this is to say that from the track object you can access a lot of information about the properties of the particle updated to that step. So as I was saying, the track is kind of a photo of a particle which is updated every time. So you have a track, G4 track here. Then you have a new G4 track here, which cancels the previous one. And G4 track contains the kinetic energy, particle type, particle time, position, volume. So most of the information that you want to get are from the G4 track. So here, the G4 track will give some energy. After the step, the energy is updated, will be lower because you lost some energy in the step. So here, the photo of the particle is updated throughout the stepping. So the way GEANT4 handles information retrieval is the so-called sensitivity. So you can mark some of the detectors, some of the volumes. You have a logical volume which can have a property called sensitivity. This just means, okay, dear GEANT4, this is a volume which is interesting for me. So treat them a bit differently from the others. So this is the meaning of sensitivity. It's just a flag which is attached to a volume saying that, okay, this is a special volume for me. It's not like all the others. So do something more. So from a technical point of view, sensitivity, it means a pointer to a G4V sensitive detector. So here you see that V, here is a V, so it means that a virtual base class. So it means that the sensitivity has to be implemented by yourself. So sensitivity may mean a lot of things. Sensitive to what? To position, to energy, sensitive. So the kind of sensitivity, it's something that GEANT4 cannot know by itself. It's up to you to define that it is, I don't know, a tracker, so it's sensitive to position, or it is a calorimeter, so it's sensitive to energy. So the specific quantity that you want, it's something that you have to define. It cannot be a GEANT4 default. So that's why here there is a V, and you really have to implement some code to define which kind of sensitivity do you want from that detector. Of course, there are commonly used cases. So typically you need to know the energy in a detector. So this is a common case. At GEANT4, it's taking care of that automatically if you want. So there is something which is ready for the use if you want to do something which is quite common and quite easy, like the energy in a detector. So if you need to do something which is easy enough, GEANT4 has a ready solution for you. If you need to do something which is not common or very specific of your experiment, you have to write the code. For instance, in some cases, you want to know how wide is the energy distribution of, you have a detector, you have a decay nit, and you want to know which is the typical radius where the energy is released. So this is not a typical case. The typical case is the total energy. But here you want to know which is the average radius in which the energy is released. And this is something special that you have to do by yourself. So it's not something which can be provided ready for the use by GEANT4, but you have the flexibility to do whatever you want. So the cost is that you have to do some coding, then the pro, of course, is that you can do more or less everything. So you can cook up the information in a more general way. So this is to say that there are two possibilities. The first of all, that you create your own sensitive detector in which you define what's your meaning of sensitivity, so what you really want to do. So it's very highly customizable in the sense that you really can do whatever you want. The second option is that you use some of the tools that GEANT4 has already inside and that are covering some common cases. So if your case is what GEANT4 has, that you can use it. Otherwise, you have to write your code. So the way to add the sensitivity to a logical volume is just 2 lines of code. So you create an instance of the sensitive detector. Here you have new my sensitive detector, and then you attach it to the logical volume. So this must be done in the function which is called construct SDN field of the geometry. So this is a virtual method, but not purely virtual. So you may implement it or not. If you have a look at the exercises, you will see that there is a function called construct SDN field in the geometry, and in which you define a sensitivity attached to the sodium iodide detector. So it's already done for you in the exercises. So the sodium iodide is marked as sensitive. And I'm not using a custom sensitivity, but I'm using a sensitivity which is one of those which is provided by GEANT4 by default. So the sensitivity is attached to the logical volume. So the sensitivity is a property of a logical volume, not of a physical volume. So if you have a logical volume which is placed many, many times, all the copies will have the same sensitivity. So this brings me to the next step, which is describing what GEANT4 already has ready for the use. So what is called the native GEANT4 scoring. So GEANT4 is providing a few so-called primitive scorers that allows you to accumulate one specific quantities for each event. So if you need to do energy per each event, that's a fairly general case, and GEANT4 is providing that. If you want to do flux for each event, it's also something which is fairly general, and GEANT4 is providing that for you. So if your task is easy enough, you can use this GEANT4 ready for the use tools. So the example that you have, it's really using those tools, because I just need an energy in the sodium iodide. So this is an easy case, and this can be handled by the GEANT4 tools. If you have something more complicated, it's not guaranteed that you can use out of the box the GEANT4 functionalities. So what is used in this case is the so-called G4 multifunctional detector, which is actually a derived class from G4V sensitive detector. So it's a concrete implementation of a sensitive detector, which you can attach to a logical volume. So this is a specific sensitivity. It's a kind of sensitivity that you can attach directly to the logical volume. Then you attach this multifunctional detector, and you have to specify which quantity you want to score, typically energy, dose, flux, and so on. So this is pretty general. So you attach the multifunctional detector to the logical volume, and you say which is the quantity that you want to be scored. So this is generating automatically a set of so-called hits in memory. So you are saving automatically some information in the memory, which is made available at the end of each event. I'm coming to this later. So suppose that we want to know, we have a volume here. which is interesting for us, and we want to get two information: the total energy, which is released in this volume, and the total flux of particles, which is coming through this volume. So this is our goal of the simulation. We want to know the energy which is released in this and how many particles they get into this volume. So this is a fairly general case. So first of all, we create an instance of the G4 multifunctional detector. We say that our volume is sensitive, so we attach this sensitivity to the volume, and then we say, okay, I want to register the total flux, and they want to register the total dose. So we use the scorers that are called flat surface flux to register the flux, and dose deposit to register the energy. So we have two sensitivities, let's say two quantities that are registered, the flux and the dose. This is the general way to do that, and this is actually, you see it's only a few lines of code. You instantiate the multifunctional detector, you attach it to the volume that you want, and you have to specify what's the kind of quantity that you want to register. So there are a few quantities that are already provided by GEANT4 that you can register. You can look at the manual. So you can register the energy deposit, the surface, the number of secondaries, the total charge which is generated in the volume, how many, the average track length. So there are a few general purpose quantities that you can retrieve more or less out of the box from GEANT4. You also have the two version of currents, so you can calculate the flux in a scalar way, so whichever angle it counts 1, and you can also use the vector definition of flux, so that each track is weighted with the cosine of the angle. So you can do both of these things, counting as scalar or counting as kind of vector. You can do also something more. Maybe you want to know the flux, but only of gammas. You don't care about other particles. You want to count only gammas. So you can attach filters to your scorers to select only a certain type of particles to be considered. So you can accept only charged particles, you can accept neutral particles, you can accept particles in a given energy range, you can accept particles of a given kind. So you can customize a little bit those scorers by adding filters. So this is the typical case. You want really to know the number of gammas entering in your detector, and you don't care about electrons or whichever. So this can be still done using the GEANT4 scorer by using the filter. So as I was saying, what GEANT4 does in this case is that every time for every event you have energy, you are entering to this special volume, you save energy and flux for every event. So you have event number 1, event number 2, event number 3. In the real case, this information is kept in memory, so you have to read it before it's gone. So when you start the second event, this information is cancelled by GEANT4. You are not keeping it in memory forever. At the end of the event, you have to read it by yourself and write it in your file or whatever. So GEANT4 will make this information available, but you have to read it before it's removed from the memory. And this is the way it's typically done at the end of event action. So it's something that you want to do at the end of event. So there is some kind of code which is copy and paste, in which you retrieve this piece of information by name. So this is the name of the total surface flux, which is what you gave here. So these things are mapped to a name and surname. So you have the name of the multifunctional detector, which is the string which you give here, and the name of the quantity, which is the string that you give here. So you have two quantities that are marked by strings. And at the end of the day, you have to go and read the information. So dear GEANT4, bring me the information which is called this name and this surname, and you read it. So this is the least easy part in GEANT4, which is really retrieving the memory, the information, and then making it available to be written on file. Still, you may have, suppose that this is a logical volume, and this is placed many times. So you have 3 copies of this volume. So GEANT4 will keep the energy separately for these 3. So what we have here is not E and phi, but it's E1, E2, E3, phi 1, phi 2, phi 3. So the most general way is that you have to read out a vector here, not a scalar, because you may have many copies of your logical volume. Remember that the sensitivity is attached to the logical volume, not to the physical volume. So you can have many copies of the same volume within the geometry. So this is what this is. This is a loop, and this is actually looping on the copies. So in the easy case, this is not a loop. You have only one entry. So this is E and phi. In the most general case, you have a loop because you may have many copies. So this is more or less copy and paste. So you find it done in the event action. So this piece of code, it's in your event action, and in the function which is called end of event action. So this is something which is done every time a new event is over. So when an event is over, before cancelling this memory, you read out the information which is in the memory. This is done at the end of every event. And then what you do, in the specific case of the example, you put the energy into an histogram. So some of you have already seen that there is an output file produced by the simulation, which is called uc.root, which contains an histogram, which is the histogram of the energy deposited into the sodium iodide detector. So the procedure which I'm following in the example is that I have the sodium iodide detector, I get the energy which is released for that event, and I put it into the histogram. So that's a way of saving result. GEANT4 will not save anything for you. So it's up to you to decide which is the number that you want to save, retrieve it, and put into the proper file, or the proper histogram, or the proper format. So that's not very friendly, I understand, but it's providing the most of the flexibility. So it's up to you to define, to retrieve the information that you want, and to make sure that it's written on an output file. So for a very long time, GEANT4 did not make any attempt to provide any support for analysis. So this is a Monte Carlo code, so we do the Monte Carlo and you take care of writing the results. So these things changed a little bit in the past few years, so that GEANT4 is now providing some basic analysis tools like making histograms or n-tuples trees. So now you can also write some kind of output format. Still, GEANT4, as I'm saying, GEANT4 is providing some basic method for analysis in which you can write output in a root format, XML, HBook, or ASCII, so comma separated, which you can read also with Excel. So this is appropriate if you want to do something which is very quick. In my case, I wanted to do just an histogram, an energy spectrum, so it was perfectly fine with me. On the other hand, depending on what you are going to simulate, you may go for an ASCII, so human readable, or for a binary, which is not readable but may be more efficient from the point of view of storage. So you have many choices that you can do the comma separated or root file or whatever. This is still up to you which kind of format you want to get from your simulation. If you are producing very large files, it's not very efficient to have them in ASCII or human readable. You rather go to binary format. Okay, this is what I had for the first half of the lecture. Then we take a break, a coffee break, and then at 11 I will give the other half of the lecture, and that's it. Take a break.